Hey everybody, my name is Luke Metz, and I'm here to present, why is it doing this? I'm here to present some work I did with Ben, David, and Jascha called Unrolled Generative Adversarial Networks. So as many of us know, GANs are notoriously hard to work with. In this work, we wanted to try to address some of these issues. First, they're very unstable during training. We hypothesized that this was due to a disconnect between the original GAN theory and what's commonly done in practice. Next, once successfully trained, the generated data distribution from the generative model only covers a subset of the original data distribution. It picks the most prevalent nodes, models those, and drops everything else. While this is nice and creates very visually appealing samples, it's not necessarily an ideal property for our generative models. So to introduce our technique, first consider the normal GAN optimization procedure, or the normal GAN objective. The goal is to find the optimal generator parameters, theta g star, that satisfy the following min-max equation. We can do a simple substitution by replacing the inner max with some function that is the optimal discriminator, which is theta d star. Next, we can perform an approximation of this optimal discriminator by, instead of doing the complete max, we approximate it by just taking a few steps of SGD, maximizing this f. And then when training the generator, we now backpropagate through this optimization procedure. So why does this make sense? First, it's more closely aligned to the original GAN min-max problem. Instead of just taking the current discriminator parameters and calling those the max, we instead do some computation to try to better approximate this max. Next, the generator is able to respond to how the discriminator will react. Instead of, the generator can almost see into the future almost. Instead of just taking the best move at the current moment, which is collapsing to a mode of D, it can see what's best for it to do multiple steps ahead. So to demonstrate this, we constructed a toy 2D example trying to fit a mixture of 8 Gaussians. In the standard GAN setting, the generator probability mass rotates across all the valid modes. This is obviously not ideal, as it never converges. In the unrolling case, however, this can no longer happen. If the generator were to take a small move with all its probability mass, the discriminator could quickly respond and solve that. Whereas instead, the generator has to make something that's hard for the discriminator to react to, which in this case means spreading its probability mass out and then converging to the correct distribution. The next phenomenon we wanted to look into is mode collapsing. We wanted to see if there were any examples from the original training data set that the generator could not successfully reconstruct. As many of you all know, GANs don't have any form of inference network, so we resorted to an optimization procedure to try to find the best Z, the best latent code Z, that minimized mean squared error to some target image. You can see some examples of this on the right, where the zero-step GAN, or the zero-step case is just a standard GAN. The reconstructions are quite poor. Take the orange truck, for example. It changes the color because the generator can't create orange trucks. Whereas when we add unrolling steps, many more of the modes are preserved and the reconstructions are better. I want to thank you all for listening, and if you have any questions, feel free to stop by our poster.
Hi. Have you tried using adversarially learned inference or ByGAN or any of these approaches for the reconstruction errors?
I have not, no.
Any intuition?
From my little bit of experience with the standard ByGAN, I found that there was a large mismatch between the reconstructions and the original data. My intuition is that doing unrolling would probably help because it's going to allow the generator to model more of the distribution. But I'm really going out on a limb. I really don't know.
Okay, thanks.